On the left side of the screen, we've got a really long line. And I'm saying that this very long line has a charge density lambda. As a reminder, that charge density lambda is how much charge there is in some length of it. So if we consider a small portion of this, we're considering only a small amount of the charge. And if we consider a larger section of it, then we're considering a larger portion of the charge. Okay, I'm going to rewrite this a little smaller. Okay. Since this is a Gauss's law problem, I'm going to want to enclose some charge with a Gaussian surface. The Gaussian surface I'm going to draw in a different color because it's not a real surface. It's something that's just mathematically drawn to encompass the charge and to try to make it clear what charge we're talking about. Since I'm dealing with a large line, it's naturally best to surround it with a cylinder. So make a hard line for the front edge, dotted line for the back edge. Alright, that's about as good as I can draw a cylinder. I'll make this solid as well. Alright. Next, how much electric field is pointing through this surface? Well, the electric field, which I'm going to do in dark green, is pointing away from the surface. This includes towards us and away from us, and left and right. Okay. I want to note how much of that electric field is going through which area. Okay. It is not going through, let's see, good color here. It's not going through this area up here. And it's not going through this area up here, down there. Instead, it is only going through the part of it that looks like a toilet paper roll. Just that portion of the cylinder. Okay. I need to know the area of that part of the Gaussian surface. The area of the Gaussian surface, okay, well, that will be this length multiplied by this circumference. Why that circumference? Well, imagine that you roll this thing out. If you roll that thing out, so you just cut it right down the line here, spread it out over here like so. This is the circumference, that's the length, and this is the area of our edge of the cylinder. Okay. More specifically, it'd be length multiplied by 2 pi r, where r is that length right there. The distance from the charge all the way to the edge of our Gaussian surface. Next, Gauss's law. Gauss's law says that the electric field pointing through some area is equal to the charge enclosed by that Gaussian surface divided by the permittivity in that region. And it's going to be free space for our purposes here. All right. this Q enclosed, well, that's going to be a callback to there. So Q enclosed will be the charge density per unit length multiplied by the length. I'm going to rewrite this. Electric field multiplied by area of the Gaussian surface is equal to charge density multiplied by length divided by the permittivity of free space. The area of the Gaussian surface is that L2 pi r lambda L over epsilon naught. There's an L on both sides, and I'm going to cancel those out. And I'm going to divide 2 pi r to the other side. And I get that the electric field near a long line of charge, sorry, some motorcycles just went by, not sure if you heard that, is equal to lambda divided by 2 pi epsilon naught. And I'm doing the 1 over r separate. I'm writing it separately because that's a really important part of what's going on here. The electric field decreases the further out we're considering. Okay. I'm going to add one more thing. It's outwards. Okay. The electric field 2 pi epsilon naught 1 over r in the r direction. That is our electric field near a very long line of charge. If it is positively charged, then it is outwards. If it is negatively charged, it is inwards. The green lines I drew on the left is assuming that it is a positive charge. There we go. That's our first derivation.